Right, the first thing about worksheet K is understanding what is actually taking place with this wheel spinning. They reference these initial angular velocities, these linear velocities at the edge. They talk about velocity of the center of the wheel at different places. So it's really important to read through this paragraph and then kind of visualize each part. Just before, when they say t equals 0, or basically just before this thing hits the ground, the wheel is spinning in place but not actually in contact with the ground. So it's not moving across the ground with translational velocity, it's just hovering over the ground and spinning around and around in a circle. Then this says an interval of between 0 and capital T being when the wheel actually catches and rolls without slipping. So that's when there's no more sliding friction taking place. It's all static friction. And at that time, there's some forward motion taking place. It's less than the initial velocity of a particle at the edge here. So the whole wheel is starting to move forward, but it is kind of skidding over the surface. It's skipping and sliding. Think of like when a car burns out and just kind of spins its wheels on the pavement, and the wheels are being dragged across the pavement, and that's going to result in the pavement pushing back with kinetic friction, not static friction. Static friction is how we normally are supposed to be driving, where we're not skidding our wheels out, we're just gripping the road, and then that static friction pushes forward. In this case, it's a kinetic friction pushing forward that's allowing this thing to start moving forward, but that kinetic friction also slows down the velocity. Then after T equals capital T is when we have all static friction pushing on the wheel instead of the sliding friction we have going on at this step. After that time period T, the wheel is just rolling with static friction forward. So I have a little video to help visualize this, and we'll show that next. Alright, so this first part of the video, we are going to set up the conditions that would be when T, right before T equals 0. So before I've set that wheel down, this thing is spinning with rotational velocity. Just to kind of help diagram that out, it's got the spin going on forward. So if I were to let it go, it's going to spin away from you. It's going to go towards that door in the background. And there's no translational velocity. I'm just holding it in place. So I don't have any linear velocity across the floor, just angular velocity. Then we're going to hit play the video. There's this period of time here where it's skidding across the surface. So it hits the ground and it starts skidding across the surface on the ground. And this would be like the middle section of, it says like when in between time of 0 and capital T. And then if we keep playing that video, so it is moving forward with a little bit of linear velocity here. That would be like that tangential velocity. And the last step would be like where it hits capital T. I'd say that happens right about there. Capital T, now the wheel is not sliding anymore. It's just gripping the surface and moving forward. And you can actually see it takes off pretty fast once that happens and smacks the back wall. So using that information, we'll go back to the worksheet and kind of try to diagram what they're representing. The first thing they want to know is, well, what's happening at that moment when this interval here of in between time of 0 and time of capital T, when it's sliding on the ground with sliding friction and moving forward a little bit, and how would all the forces look on the object in that case? Well, we can start with our obvious one, the force of gravity, and that's straight down. And because this is a free body diagram, a force diagram and not a free body diagram, you're supposed to draw the forces at the point of contact. So there is a normal force back up, which would start to overlap this weight. So I'm just going to draw it right off to the side just to be clear about where it's happening. But that normal force back up is equal to the weight of the object down, and those are offsetting each other to balance out. The thing that we have additionally in this problem is this frictional force, which in the last worksheet, worksheet J, it was static friction pushing forward, but this case it's slipping and sliding, and so it's the force of friction, but this is kinetic friction. And that kinetic friction forward is responsible for actually making the center of mass of this wheel start to drift forward, and eventually it's going to attain a value of half of the initial velocity of a particle on the wheel rotating at that distance. So in part 2 it says, in terms of the forces you drew, explain why the center of mass increases in speed and rotational speed of the wheel decreases during that same time interval. So the wheel is going to pick up translational velocity, but it's going to lose rotational velocity. And to help understand that, it's all based on this guy right here. This frictional force kind of does both. If you think of translational motion, there's an unbalanced force to the right in this problem. There's no forces backwards on the wheel. So the wheel is pushing into the ground is shoving backwards with frictional force. It's kinetic friction because these surfaces are sliding past each other, but it is still a force to the right that's unbalanced. And because of that, the center of mass of this wheel is going to start to pick up velocity in the linear, in an x position, in a linear sense. But at the same time, that force is applying a torque. And so if you think about the radius away, I'll just kind of draw another version of this. If that wheel is experiencing a force at a radius away, that's going to equal a torque that's trying to counteract the rotation that was already started. This initial omega was forward, and this counter torque would be working against that. So that force is providing a torque that's counteracting the angular velocity of the wheel, and so it's doing both things. It's helping speed up the center of mass to the right, but it's also slowing down the rotational speed of the wheel as it goes. And that's all about conservation of energy. Basically, that force is, if it's going to help speed up one part of it, it's got to slow down another part of it. We can't get energy from nothing. So this one's a little tough to figure out. Why is it that this equation is not valid? It's confusing. I mean, I've never seen an equation that has mu and omega and radius and gravity in there. And we're not going to really take the time to derive the full thing. We're just supposed to look for a way to figure out that it's incorrect just by concept alone. The first attempt I did at this, to like, maybe the units were off, I tried to look and see, do those units actually give you seconds? And I found out that they do. And so looking at the units alone isn't enough to understand what's wrong about this equation. But I started then thinking about, okay, is there any variable that's in this that would not give that time t, like not make sense for the time t? And starting with that very first variable, that's where we go wrong right away. So here's how we can understand this. If the time t is the time it takes it for it to like start gripping the road and then just travel with static friction force, so it just kind of continues on its path and gets faster and faster in that way, so no more sliding basically is what happens at time t, then we have to see, like, do these things actually directly impact that time it takes? Well, the coefficient of sliding friction, mu, that's coming from the fact that force of friction, kinetic, equals mu times normal force. If mu goes up, the force of friction would go up. So the way that they have this, it's directly related in the formula. So what we're saying then is that if mu goes up, the force of friction goes up on that wheel. So if you have more force of friction, you're gonna get to be rolling without slipping faster, or like basically in less time. If this is a larger force, you're gonna get up to the speed that you need to just roll without slipping in a quicker amount of time. So we're gonna get to that time t actually faster, or it'll take less time to get up there if we had a larger force of friction. So the way they have it set up in the formula is just not in the correct spot, because what they're saying is that if you have more mu, you'd have more frictional force. And having more frictional force, they're saying that's taking more time to get up to rolling without slipping. When in fact we actually want mu to be down below, which should be an inverse relationship. So if mu goes up, there's going to be less time it takes to start rolling without slipping. Think of it like this: the better that friction is between the road and the wheel, the quicker that car will get up to speed. It'll start gripping that tire better and better so that it can just roll without slipping. What's happening when it has really low friction, if coefficient is really small, then time period is going to be very large, meaning it's going to take a long time to just stop skidding across the top and finally getting up to rolling. And I don't really have a way of showing this other than if I did it with that metal wheel. Let me just play this video one more time. With that metal wheel, it slips. And I want you to imagine if I used rubber on that same surface. Okay, if I use rubber, stop, there we go. If I use rubber, it would grip higher. There would be a larger coefficient, so coefficient would be bigger. That would lead to more force of friction, and that rubber tire would grip the road better, and we'd be up to rolling in a shorter amount of time. So there's a lot of different variables. I just want to make sure, but there's less T if you had higher friction, and that's why the coefficient should really be down in the bottom, and that's why that doesn't make sense. I tried to check out the units, but the, coefficient doesn't have real units, so it doesn't matter if we put it on top or bottom, because coefficient is just a unitless ratio. So it doesn't mess anything up if you move it down to the bottom, but that's where it should be. All right, so now Dominique's switching out different surfaces, and she sees that no matter what, you kind of always get back to this eventual, that the linear speed increases to a half of the initial velocity of the wheel, and the rotational speed drops to half of its initial rotational velocity. I think it's easier to start with the fact of rotational velocity. That was initial omega. When it was just spinning above the ground, that had a full value of 1 initial omega at time equals 0. And then it hits the ground, and that initial omega slows down. And when we're in section 2, it was skidding on the surface here, and now we had omega that was less than initial omega. And by the time it gets to that full time t, now your omega equals half of the initial omega. So we got the wheel moving that way, and it's still spinning, but it's spinning at half the rotational speed that it was. So let's just say for we got to have the kind of two systems. I'll do two different colors. Green will be part I, a table that has low coefficient of friction. If it has low coefficient of friction, it's going to take a large amount of time in order to get to get to half of the initial velocity. So t is going to be a lot larger. So I may be just going to take a long time to get to half of the initial velocity, and then I'll flatline it. And it's the same concept with, let's draw red for 2. I'm still going to start with that same initial velocity there. It's just I'm going to get to half initial omega much faster if I have a high coefficient of friction. So it's going to take way less time. And this is getting back to the idea of if you have time dependent on 1 over the coefficient. If that coefficient goes up, my time it takes to start rolling without slipping goes down, and therefore the red will get to that spot quicker. Like this is its capital T, whereas the green one takes up to here to get to its capital T. So if capital T represents the time it takes to roll without slipping, then they take different amounts of time to get there, and the one that's slipperier, is that a real word? Whatever. The one that's more slippery, the green line in this case, with low coefficient of kinetic friction, that is taking more time to start rolling without slipping. Now we do the same thing in reverse. The center of mass of that wheel for green is, it's kind of the reverse of what we just drew. The center of mass is going to take more time to get up to speed of a half of the linear speed. And so I would just start from 0. And let's see, I took 1, 2, 3, 4 blocks to get up to, so I've got to take the same amount. So it's going to go like this, and then flat line. So straight line down to there. Whereas the one with high coefficient is going to get to half right away. So we're going to basically get up to that speed that we're talking about in a much shorter time period. Again, that's capital T. This would be the green one's capital T. So you come up with your own labeling system, dotted lines, straight lines, but that's how that part C works. All right, I'll see you in class.